Okay. Good morning, everyone. Hope you're well and ready for the sixth lecture in this series of introductory radio astronomy lectures. Today, I'm going to tell you a little bit about antenna theory and the basics of how radio telescopes work, with the interest that we start tackling interferometry from the next lecture. So this is a bit of a lead up to that. So at the end of this, you should have some sense for how antennas work and the different types of antennas that exist. You should understand the concepts of aperture and radiation pattern. Those are very important concepts, and you should know how they are related to one another. You should also be able to recognize the different kinds of parabolic antennas that we use in radio astronomy. And you should know some factors that determine the efficiency of an antenna in receiving signals. So let's start from the beginning. When we're talking about radio astronomy, the single biggest factor to consider is usually the fact that radio photons are very low energy. So to give you some idea, 21 centimeter radio photon, that's equivalent to about 5.9 micro electron volts, or about 10 to the power minus 24 joule. To give you some sort of scale, I looked this up. A single grain of rice has about, I think, 30 calories, which works out to about 88 joules worth of energy in it. So a radio photon has 26 orders of magnitude less energy than a single grain of rice. So it's very, very low energy. And it's even weaker than other photons at other wavelengths. It's 100 times 1,000 weaker than a typical optical photon at 500 nanometers, a billion times weaker than an X-ray photon at 1 nanometer, and about 100 quadrillion, or 10 to the power 17 times weaker than teraelectron volt gamma rays, which is about 10 to the power minus 18 meters. So high energy astronomers, which are looking at X-rays and gamma rays, they can use single photon detectors, such as photomultiplier tubes. These are instruments that produce basically an electrical signal when some photon falls onto the instrument, usually using some quantum effect, particularly the photoelectron effect, the photoelectric effect, which says that if you have a photon incident on a conductor, it might knock loose an electron. But radio photons are just too weak to produce any of those kinds of effect that would allow us to count them individually. So we can't count radio photons, but the advantage that we have is that there are a lot of radio photons. Because they're so low energy, it's easy for a source to produce a huge amount of radio photons. And what we can do is to measure the aggregate effect of all of those photons on a conductor, for instance. So we can observe a conductor, like a thin piece of wire, which we call an antenna. And then as radio waves are incident on that thin piece of wire, it induces oscillations of potential that we can then measure. And that's how we can observe radio waves. So this at the top is a typical antenna that should be familiar to you. Just this the one kind of uh, 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 metal rod type antenna that you kind of see on portable radio systems, that kind of thing. That's called a monopole or whip antenna because it just has the one pole. A slightly more complicated version of that is the dipole antenna, which is the the rabbit ears that we used to put on televisions, as you can see down there. And this animation shows you exactly how that antenna is measuring a radio wave. So we have this antenna made up of two poles, a dipole, basically two conducting rods in parallel to one another. And there's an electromagnetic wave incident on that. And the green shows you the amplitude of the electrical field. And as that electrical field passes the conductor, it moves the electrons within that conductor, causing a surplus of negative charge on one end and a deficit on the other, basically inducing a potential difference across those two poles, which we can then measure. And that potential difference is varying along with the amplitude of the electric field. So in this way, we turn the electric field from the radio waves into an oscillating voltage with the same frequency as the radio wave. Now this is a more elaborate version of that. On the top left is an antenna called the Yagi-Uda array. And this is basically some dipole antennas arranged in parallel. And the important thing about this is because these are all working together, it's a directional antenna. So it's only able to send and receive signals in a particular direction. And this animation on the right shows you how that works. So because there's a spacing between those antenna elements, at some points in the radiation field, the radio waves will be interfering constructively, and at other points they will be interfering destructively. So it will only be able to send and receive signals in the direction where those signals are in phase, where they're interfering constructively, and that's how you get a directional antenna. On the bottom left here shows a log periodic array, which is basically a bunch of Yagi-Uda arrays stacked on top of one another. But you can see that there are different lengths of these horizontal rods, and the length of those rods corresponds to the wavelength that it's able to receive. So using this kind of setup, you can receive multiple different frequencies at the same time. The next elaboration on that is called the phased array. So you have a row of antennas all lined up as shown on the left here, and you have some computer controlling or phase shifter that adds delays to the signals from each of those antennas. And by being clever with those delays, you can effectively move or change the direction of this wave front that forms where they interfere constructively. And so you can, and then the phase shifter, by changing those phases, can point the direction of this antenna without actually having to move any of the antenna elements. So you get an effect like the animation on the right is showing there. And in fact, some radio telescopes use the same setup called a phased array feed in their receiver, where instead of having a single receiver, they have an array of receivers like this, and that allows them to form multiple beams on the sky at the same time. So they can essentially form like a fly's eye view of the sky, observing different points in the sky at the same time by manipulating these delays. So I think ASCAP, for instance, and um, which is the other one? Uh, Effelsberg maybe has a phased array feed. Right. So another kind of antenna is this horn antenna, where instead of a cable, you have a horn that feeds a coaxial cable. So only radio waves that are coming in the direction into the mouth of the horn are received. And so that's how you create directionality just with this physical structure. Um, and a very famous horn antenna is shown on the right here. This is the antenna that Penzias and Wilson used in 1965 to measure the cosmic microwave background. So they didn't use a dish telescope like we know today. They used this gigantic horn structure. And you can see that there's a wheel surrounding the horn, and that wheel allows it to turn. So the horn could be rotated up and down to point at different regions in the sky, and that's how they mapped the CMB. That's very cool. And today we we don't really use these horns by themselves anymore, but telescopes like Meerkat use what's called a feed horn. So you have a dish telescope, which I'll show you in a few minutes, and then a secondary reflector, but then the receiver of the telescope before that is a horn shape, and that the function of that is to uh, further shape the beam that you're able to observe to exclude any radiation that you don't want to see. So we still use this in principle, but in concert with dish antennas. What are the benefits of using this kind of receiver is that it's extremely broadband. You can use it at all different types of frequency, unlike, for instance, a Yagi-Uda antenna, which we saw the wavelength that it's able to observe depends on the length of those horizontal rods. This one can observe any kind of frequency. And it's very easy to calculate the aperture efficiency to model the signal of the beam. There are minimal side lobes and no ground emission contamination because it's so directional. And this makes it the ideal antenna for accurate measurements of weak radiation. Right, so parabolic antennas are antennas where you bounce the radio waves off of a parabolic dish towards a focus where they're collected by a feed, which then measures the oscillating voltages. So that's the typical DSTV satellite dish, is a parabolic antenna. And yeah, as I said, telescopes like Meerkat use a horn antenna at the feed, which is called a feed horn. Right. So a very important concept in antenna science, and which we will be using again when it comes to interferometry. So it's very important to understand this, is the concept of radiation pattern of an antenna, or also called an antenna pattern or beam pattern or far field pattern. There's different names. But all of these refer to the directional dependence of the antenna sensitivity. So uh, even a simple monopole antenna is not equally sensitive in all directions. There are um, points in the radiation field that are in phase that interfere constructively to form maxima, and elsewhere there are minima where they interfere destructively. And the pattern of the sensitivity depends mostly on the shape of the antenna and then also the shielding that you apply to keep any other radiation out. And then a related concept that's also very important is the aperture of the antenna. So that's defined as a plane surface near the antenna, perpendicular to the direction of the maximum radiation, through which a major part of the radiation passes. So this is a bit difficult to explain in terms of, for instance, a dipole antenna, but it's fairly easy to understand this for a dish, for a reflector dish. In that case, the aperture is just the hole in the feed horn that the radio waves are reflected into. That's essentially what we consider the aperture. Um, and um, the radiation pattern or the beam is the diffraction pattern that's produced by radiation passing through that aperture. So if we have a dish telescope with a feed horn, the radiation pattern that we observe from that antenna is the diffraction pattern of the light going through that hole in the feed horn. And the mathematical relationship is that the radiation pattern is given by the Fourier transform of the aperture. So if you have, for instance, on the left here, you have a circular aperture, which means in cross section, it's kind of the square function. Then the diffraction pattern, which is the Fourier transform of that aperture, gives you this varying pattern of a maximum at the middle, and then minima, maxima, minima, maxima. That's called an airy disk function. And if you take the cross section of this diffraction pattern, you see there's a main lobe in the middle. It's called the main lobe, or the primary lobe, or the primary beam. And then there are these smaller maxima, these wobbles, which are called side lobes. And in radio astronomy, side lobes are bad. They introduce information from outside of the area that you're really interested in. So you point the main lobe at the object that you're interested in, but if you have these side lobes, they can contaminate your data with information from outside of your target region. So radio telescopes are designed to minimize the effect of those side lobes. So this is an example of a radiation pattern for a dipole antenna. In the bottom left here, you see there's an antenna inside here, and then the radiation pattern is this donut shape, this spherically symmetrical donut shape. At the top, towards the top and the bottom of the antenna, there the radio waves are interfering destructively, so it doesn't have any sensitivity parallel to the dipole. And then radially to the dipole, it has this donut shape. So a very important principle with these radiation pattern is that the pattern broadly reflect the symmetry of the antenna. So here we have an antenna that's radially symmetrical, right? So it's the same in all azimuthal directions, meaning that the radiation pattern will also have that reflect that radial symmetry. Now this is the radiation pattern for a Yagi-Uda antenna. And here you can see this principle of the major lobes, and then which is in the direction where it's most sensitive. So it's directional. It's most sensitive parallel to the antenna and in one direction. But there's also a back lobe where it's a little bit sensitive in the opposite direction, and then there are these minor lobes or side lobes. Yeah, and here you can see in the bottom left a projection of that pattern in the horizontal and vertical planes. Now this is the pattern for a horn antenna. Here you can see that the back lobe is significantly suppressed. So because we have this waveguide, this physical structure which keeps out radiation from a particular direction, we are significantly suppressing the back lobe, but there are still these side lobes coming out of the sides. And if you take a look at um, uh, the uh, the two-dimensional version of that, it looks like a main beam and then these side lobes with decreasing amplitude going out. This is the radiation pattern for parabolic antenna. The big thing here is that the bigger the dish, the narrower that beam. So using a very big dish, you can produce an extremely narrow beam with very little back lobes because of the dish. But there can still be side lobes, as you can see on the bottom, um, which introduce radiation from outside the intended target. But a major reason for using parabolic antennas in radio astronomy is that there are clever designs that we can use to minimize the impact of these side lobes. Right. So next I'll show you some different types of parabolic antennas. First, there are two ways to mount the antenna. There's, as you can see in the bottom here, there are equatorial mount antennas and altitude over azimuth mount antennas. So an equatorial mount antenna is sort of mounted onto a slanted arm, and that mount is parallel to the axis of rotation of the Earth. The benefit of mounting it this way is that as you point at a source that's moving across the sky, you only have to tilt the telescope along one axis because it's following the rotation of the Earth, right? So you don't have to, so it's very easy to keep track of it. The alternative is the altitude over azimuth mount, where the mount is flat on the ground. But you have to, as you're tracking a source, you have to change the elevation and the azimuth as you go. Whereas with equatorial, you just change the right ascension essentially. So this altitude azimuth version is the cheaper type of mount. If you have done any kind of stargazing, amateur astronomy stuff, there you can buy altitude azimuth telescopes for fairly cheaply, but equatorial telescopes are always going to be more expensive. Um, so the Meerkat is an old telescope. That's an interesting. But one of the big problems with using this kind of mount is that as you are tracking a source along the sky, the orientation of the beam with respect to that source is also going to change as it tracks, as you can see in the diagram on the left. So here you can, if you look at that little peanut shape, that's the shape of the beam. And as the source is moving along that track, that's a circumpolar source, that um, orientation of that beam is also changing. And that means that there's a variation in your observation that you have to take into account. That's particularly important if you're doing polarization measurements, because remember, with polarization, you're measuring the angle at which the electrical field of the radiation is inclined. And to measure that angle, you have to know what is the angle of your beam as well. So it just introduces some extra complexity, but those are all taken care of in software. But there are different types of uh, reflector as well. The simplest kind is the prime focus uh, dish, where you have a simple reflector dish, and then at the focus of that dish, you have your receiver. An alternative to that is the Cassegrain dish, which uses a secondary receiver. So you have this um, convex secondary receiver that sits at the focus, and it reflects the radiation back towards the primary dish, and then there's a, a receiver um, located behind the dish. You can also have an offset Cassegrain, where the um, the secondary reflector is kind of tilted so that the receiver is offset. It's not quite at the center of the dish. A Naismith type uh, telescope, in that you have basically a hole in the dish, and then the signals are reflected through that hole and then further reflected towards the receiver. So basically, this means that the receiver is just it's uh, external from the telescope itself. So you can build, for instance, the receiver on the ground and then just have a series of reflectors guiding the radiation all the way towards the ground before it's received. And the same kind of principle with the beam waveguide type telescope. And then there's dual offset types as well, where the um, secondary reflector kind of sits outside of the dish and then reflects off onto a receiver that's off towards the side. So the primary focus dish is the simplest solution. There's no secondary reflector, so it's also the cheapest solution. But a big problem with that is that the receiver is very difficult to access or maintain. So if you can imagine, if you have a huge 100-meter radio dish and um, uh, the receiver is straight overhead, you have to have some sort of mechanism that allows access to that to the receiver cabin, both in terms of transmitting the signal and also to send people up there to do maintenance and make sure that everything's working. And that oftentimes is more complicated, more expensive than the money that you save from not having a secondary reflector. So the Cassegrain uses the secondary reflector, um, but the longer the wavelength, the larger that the reflector needs to be, right? Because you need to reflect the whole wave. Um, at very low wavelengths, you end up with this big dead spot at the center of the dish where the um, uh, the receiver blocks and the radiation. Um, with an azimuth or beam waveguide, where you have the physical hole in the dish, that allows you to build the receiver cabin far away from the antenna structure, for example, on the ground, which is very convenient. You can just for maintenance and that kind of thing. It's all very close to hand, but it has the same kind of problem with the dead spot caused by basically the shadow of the secondary reflector. The offset Cassegrain, where you have um, the receiver offset towards one side, that if you arrange the offset cleverly, you can minimize the loss of sensitivity by this blocking of the aperture. But because you have now an asymmetrical system, that needs to be accounted for, especially again in polarization measurements. So it's another layer of complexity, but this kind of antenna is used. For example, it's used in BLA antennas. And then there's another type of antenna that wasn't mentioned in this previous diagram, called a Gregorian antenna, and that's shown on the bottom right here. And the difference between the Cassegrain and Gregorian antenna is that in the Cassegrain dish, the secondary reflector is convex, so it's curved outwards, and in the Gregorian telescope, it's concave. It's turned inwards. So Meerkat uses an offset Gregorian type dish. So on the right, you can see what the Meerkat dish looks like. There's a primary dish, which is 13.7 meters in diameter, and that reflects the radio signals onto this secondary reflector, which is convex or ellipsoidal, sorry, concave or ellipsoidal to be exact. And then it reflects it onto the receiver down here. So the benefit of using the concave reflector is that the edges of the reflector receive less radiation, which gives you less interference. So there's a slight boost in the aperture efficiency. So when they were designing these Meerkat antennas, they went through, I think, thousands of different possible designs, and then simulated and tested various efficiencies for each of those designs, and basically found that this was the most efficient way of building the antenna that would minimize minimize the effect of side lobes, and would be most um, most conducive to the purposes of Meerkat. So the design is highly optimized so that you have very high aperture efficiency and very little spillover. And then you can see on the picture as well, you have the secondary reflector, and then the light gets reflected onto these feed horns, these three little horns there, but there are three of them. And they are mounted on this rotating disc. And basically, this means that by rotating that disc, you can place different receivers at the focus of the telescope. So each of those correspond to a different receiver that receives different frequencies. So each one corresponds to the UHF band, the L band, and S band. And there's space to add some more receivers if we wanted to. So this is a very handy way of making Meerkat multi-frequency and extending the range of frequencies that we can observe at. Right. Next, I want to show you some other weird or interesting types of antennas, which are outside of the typical parabolic reflector type. This is CHIME, the Canadian Hydrogen Intensity Measurement Experiment, something like that, which is a telescope in Canada, and it's made up of the series 4 parabolic cylinders. So they are not a parabolic dish, they are parabolic in one direction and only. And that means that you get a beam that's similar to a typical parabolic dishes beam, but it's extremely elongated. It's elongated in the direction of the elongation uh, of the cylinder itself, um, which gives it a very uh, big footprint on the sky. You're able to see a very large area of the sky, but it has uh, very poor angular resolution in one direction. That's interesting. Another interesting type of antenna is called the big ear antennas. And the idea that is that instead of using a full parabola, a full dish, you just put sections of a parabola planted into the ground. So if you look at the diagram on the right, those two walls, those two sections, are kind of two small parts of a big parabola planted into the ground. And then you can tilt that uh, parabola by tilting the sections up and down. So it's a engineering wise, it's a very simple approach, but you can still get a pretty good approximation of a very big telescope. So these kinds of telescopes are still in use today. For example, the Nancy telescope in France still uses this setup. You can see the two ears on either side, and in the middle there's a processing building where all of the detection stuff happens. Yeah. There are also cross-type antennas, which is a similar principle to the big ear antennas, where instead of building an entire parabola, you use narrow slices of a parabola. So if you think about um, a watermelon, cut the watermelon in half and slice it into narrow slices. And then you have two of those, um, which each of them produces a long, narrow beam like chime. But if you put them at orthogonally to one another, you have these two orthogonal arms where they cross over. That's where you get um, a sensitive image of the sky, as you can see the diagram on the right. So Molonglo Observatory in Australia, that's still observing. They're very proficient in finding pulsars, for example. And then Northern Cross Telescope in Bologna as well. That one has a kind of T-shape setup. Right. Then finally, we have to make some considerations about what factors make a radio antenna efficient. So let's define some terms before that. The bore site of the antenna is the direction of the maximum power received. So in the diagram on the bottom left, you have a main lobe and some side lobes. We call the bore site the direction of the maximum power. So the bore site for this telescope will be right in the middle of that main lobe. So if we say that an object is on bore site, that means it's at the point where the telescope is most sensitive. Then the half power beam width is the width of this main lobe where it's at 50% of the power at bore site. So you measure where the power in that lobe is 50% of the maximum, and then the width corresponding to that, that's called the half power beam width, and that's often used as a measurement of how big the beam is. Right. Then the aperture efficiency describes how efficiently the antenna can collect signals. So it's defined by this factor eta, given by the power collected by the feed divided by the power incident on the antenna. So if you have some source of radio uh, emission, this efficiency tells you what proportion, what fraction of that radiation is it able to convert to voltage power. And this efficiency is made up of a bunch of different factors. There's the efficiency from the reflector surface. So that's how smooth is the surface. If the surface is not exactly smooth, if there are some inaccuracies or some bumps on that surface, it means that some of the radiation gets reflected into the wrong direction. And so you have a loss of the power that you are able to collect. The second factor is the reflector blockage. So, for example, if you have uh, a, the receiver at the focus of the reflector, then that receiver blocks some of the radiation from coming through to the main reflector. It basically casts a shadow on the reflector, and that causes a loss in the efficiency. But again, by moving the reflector, the secondary reflector out of the way, you can minimize that blockage factor. Then there's a spillover, receiver spillover factor, which basically comes from the fact that you can't, the um, secondary reflector has a finite size. So there's always going to be some light that gets reflected of the main dish that just passes by the edges of the secondary reflector, and you lose that the power in that um, in those signals. Um, then there's the taper of the efficiency. And this again refers to the fact that the dish is not equally sensitive everywhere. It's most sensitive at the center of the dish, and then the sensitivity gets lower, it falls off, it tapers as you go further out towards the edges of the dish, and that's called the taper. Um, and then there can be miscellaneous different factors where you lose energy as a result of systematic errors in your collection system, maybe some inefficiencies related to the horn itself or to the digitization, or yeah, some sort of inefficiency within the receiver or the transmission of the signal. That all goes into the miscellaneous bucket. So let's talk about the surface efficiency for a bit. For a parabolic antenna, the the surface efficiency factor is given by this equation: e to the power minus 4 pi sigma over lambda squared. Lambda is the wavelength of the emission, and then the sigma is the RMS error on the antenna surface. So it's basically the tolerance on how precisely the surface has to be engineered. So a typical target for this efficiency is about 70% efficiency. And if you substitute those numbers into that equation, this gives you that the RMS error on the surface has to be about equal to the wavelength divided by 20. So for an example, the Green Bank telescope, which is the biggest single dish radio telescope in the world, over 100 meters wide, it goes up to 115 gigahertz. which is 2.6 millimeters in wavelength. So if you take 2.6 divided by 20, the tolerance on the smoothness of the GBT surface is about 0.13 millimeters. So that means if the GBT's reflected tiles, if the surface is misaligned, if it's off by a tenth of a millimeter across that 100 meters of the dish, then immediately you lose 30% of sensitivity of the telescope. So this gives you some illustration of how extremely important it is to make sure that the surface of the dish is flat. And that gets more and more complicated the larger the dish that you build. So this is the GBT deals with this problem by having motorized reflector panels. So the surface of the GBT is made up of these 2004 panels, these rectangular panels, and each one is connected to an actuator motor. Every one of those 2000 panels. And those actuator motors can exactly, very, very finely measure the orientation of each panel, and then by calibration observations can make sure that each one of those panels are pointed or oriented exactly correctly to minimize the loss of efficiency due to the surface smoothness. So in order to build this big 100-meter antenna, you need to come up with all these clever solutions to um, to make up for these loss of efficiency factors. So that increases the cost as well, of course. Another important factor when you're talking about radio antennas is the pointing error. So especially if you have a big single dish telescope, it's actually very difficult to make sure that the telescope is pointing exactly where you want it to be. Remember, we're talking about in radio astronomy on the orders of arc seconds, right? Which is, you know, 1 degree. So the full sky divided by 360 degrees, and then 360 degrees divided by 3600. So it's a very tiny um, uh, resolution that we have on the sky, and we need to, and if you have this big dish, a small error in the drivers of the telescope and the actuators where it's pointing can result in a big error on where it's pointing. So a typical pointing error that we aim for is to have an error that's the width of the beam, half power beam width, divided by 20. And that gives you an intensity loss of 10% for, sorry, less than 1%. That's for a source that's located on the bore site. So if you have a source on the bore site and uh, the pointing is wrong by that factor, you only lose less than 1% intensity. But if the source is far away from the bore site, if it's off towards the half power point of the beam, then immediately you get a 10% intensity loss. So a bad pointing error can significantly reduce the accuracy on the outer part of the image. It's not such a big problem for the center, but on the outer part of the image, it can be a very big factor. Another effect is that at higher frequencies, the beams get smaller, right? So it's lambda over d, which means that at the higher the frequency you're observing at, the more difficult it is to get precise pointing. to give you some idea, Meerkat has a pointing error of about 0.64 arc minutes. So if you look at the plot on the right, those are measurements of the pointing error of Meerkat over time. And the median of those measurements is given by the dark black line. And it is pretty stable. It hovers around 0.64 arc minutes. And the Meerkat primary beam is around 65 arc minutes. So the error is about 1/100th of the beam width. So that's Meerkat is pointing pretty accurately, but because a big problem with Meerkat is because the telescope is so oversubscribed, because the scheduling of the telescope is so tight, people usually don't include calibration observations to correct for the pointing error. So oftentimes people observe errors in the observation in the image that are unaccounted for. They assume that the pointing error is negligible, but as we can see, 0.64 arc minutes is a pretty significant amount, and for the most part, that's uh, very often not taken into account. So if you are doing some work and you find your error has some sort of your image has some sort of error, especially towards the edges of the um, image, then the pointing error is very often the culprit that you have to look at. Another important factor with telescopes is the driving of the antenna. So if you have a steerable telescope like Meerkat, the speed at which it can be moved physically is very important. The reason is that it determines the observing overhead of time that is lost to slewing from target to target. So when the telescope moves from target to target, that's called slewing. And the slower it moves, the more time you lose moving from target to target. But if you have a very fast slewing, it enables you to do better calibration because you can rapidly switch between calibration sources. Now, Meerkat moves pretty fast, around 1 to 2 degrees per second. So it's much faster than, for instance, Parkes telescope. But there's a fairly significant settle time before it settles on the source. And I think that has to do with making sure all of the 64 antennas are pointed at in the same direction. So there's 8 seconds of overhead each time, which is actually a fairly significant problem. The speed of this steering is largely dependent on the weight and the stiffness of the dish, um, uh, and including the power of the steering actuators. Okay, so finally, an interesting question that I've often wondered about and that people often ask is how big can a radio telescope actually get? So one factor is that the bigger the dish, as we saw, the more difficult it gets to control surface efficiency and other efficiency factors as well. But the surface efficiency is a big problem. And remember that this gets worse for higher frequency observations, right? Because you have a smaller beam. And so for a telescope like FAST, which is the 500-meter aperture synthesis telescope in China, it's 500 meters wide. This surface efficiency is the reason why they can't go above 3 gigahertz. Above that, it's just impossible to get smooth enough of a surface on the dish. Another factor is that the degree to which the wind affects the dish scales as the diameter cubed. So for a very, very big telescope, one storm could completely ruin the telescope. For for that reason, FAST, for instance, is built into a natural depression in the ground in this natural valley, which minimizes the effect of wind. But hopefully, a lot of you will remember the Arecibo telescope, which was a similar huge telescope built into a depression on that. But they had a setup where the receiver of the telescope is sort of hangs overhead, supported by struts. And the wind and storms eventually just caught those struts and brought the whole thing down. And it's not working anymore. Many millions of dollars gone with it. So the wind is a big problem. The construction costs also scale as diameter cube. Here's a plot of the cost of small parabolas as a function of diameter. So for example, FAST cost $170 million. Meerkat is about $5 million a dish. And you can keep building dishes. It's not a one-off expenditure. You can budget to expand um, uh, the telescope gradually with an antenna array. So for all of these reasons, the future of radio telescopes very much points in the direction of array telescopes, rather than continuing to build bigger and bigger single dish telescopes. Right, so that's it from me. Let's just summarize. So we can't measure radio photons directly. Instead, we have to look at how they cause voltage oscillations in a conductor, which is called an antenna. There are different types of antenna to suit different purposes, and each one has a unique radiation pattern. The radiation pattern shows the spatial variance of the antenna's ability to send or receive signals, and this radiation pattern is given by the Fourier transform of the aperture. The aperture for a single dish telescope is the hole through which the light is reflected. Then there are different designs for the setup of parabolic antennas. Meerkat uses an offset Gregorian dish. And then a radio telescope's performance can be affected by many factors, including the smoothness of the dish surface and the accuracy of the pointing of the telescope. Cool. Any questions? I'll move straight to the questions on the chat, and then if you have any others, you can put your hand up. So, first question from Rahul, what are the side lobes? Okay, so side lobes are regions in the antenna pattern and the beam pattern of an antenna where it's sensitive as well. So if you have an antenna like this one, it has a major lobe where it's most sensitive, but then there's also a back lobe in the opposite direction, and these side lobes, which are off toward areas of sensitivity off to the side. So it's going to be very sensitive to signals coming from this direction of the main lobe, but it might also detect some signals in these coming from these directions off towards the side. So yeah, does that answer your question, Rahul?
Yes, that does. And on the figure on the left bottom, I just want to know, did you use Python to plot that?
I didn't plot this myself. There's a website, I think it's called antennascience.com or something that I got this from, but it looks a lot like Python, yeah. But there
Okay.
are software packages that we can use to simulate the Meerkat primary beam and the coherent beams as well. So yeah, we can efficiently model. We can make a plot for like this for Meerkat as well. I've done that a fair amount of times.
Okay, sir. So I just wanted to get some clarification. So side lobes are like the interference lobes. They're the lobes that interfere.
Yeah, you can think of them as sources of interference. So when we have a directional antenna, right, it's pointing in a specific direction, or dish. It receives signals only in the direction where the dish is pointing, ideally, right? But because we're living in the real world and nothing is ideal, there's some radiation that gets in from other directions, from either from the back side of the dish or off from the sides. And those are called the back lobes and the side lobes. And they contaminate your data from the main lobe with interference. Um, and then the question was the difference between an antenna and a feed. Okay, that's a good question. So in radio astronomy, an antenna is basically a synonym for the dish. So this whole setup, the primary dish and the secondary reflector and the receiver down here, all that is called the antenna. It's just a collective term for the whole thing. The feed specifically is the part of that antenna where the light is collected and turned into a voltage. So in this meerkat antenna, these horns, these those are the feeds, and they collect the radio signals and they send it to a receiver, which digitizes, measures the voltages and digitizes the signal. Does that make sense, Paul?
Perfectly made sense. Yeah.
Cool. And then, which efficiency factor does ohmic losses count as? Yes, I think ohmic losses is going to be a significant factor in this miscellaneous factor. I think all of the kind of effects that are to do with transmitting the signal all go into this miscellaneous factor. Any other questions or comments? Okay, not seeing anything on the chat. So in 2 weeks' time, we're going to start with the basics of radio interferometry. And some of these concepts are going to be very important. So um, in interferometry, we use a technique called aperture synthesis, right? Which means that we used uh, a bunch, an array of different antennas or dishes to synthesize the aperture of a single telescope. So we use many different telescopes put together to synthesize or to make one big telescope. And then the Fourier transform of that aperture gives us the beam of the collected telescope. So just make sure that you understand that concept before next week. It's very important. Yeah, if there are no further comments or questions, we'll leave it there and I'll see you in 2 weeks. Okay, cool. Okay, thanks everyone. Cheers. Have a good weekend. Bye-bye.
All right, sir.
Guddaan kan taatee fi yoon nagaraa laafnaa